come in and do a presentation today on some of the basics because I realize that some of the videos that I release are more on the advanced side, and I realize that some of my viewers, some of it may go over their head or they just may not understand it. And to know some of that stuff, you have to really understand some of the basics, at least some of it, you know what I mean? And so I figured I'd come in and explain some of the stuff that I know. And I by no means know everything about all this. So I know there's people out there that may watch this that do know more than me, so just stick with me, and if there's something I get wrong, feel free to go in the comments section and let me know. But just be kind about it. We're all trying to learn and share information and trying to understand the world. You know, even the scientists, they're all trying to understand. What we have before us is the basic periodic table. And if you kind of recognize this, then you probably learned about this in science class in school, you know, back in school. And some of you may have taken, you know, chemistry or some sort of more advanced science in school, but this is pretty much taught to all of us, so this should be kind of familiar to most of us. So hopefully this will be a kind of a review, and we can kind of get through this. And this is basically off the cuff. I don't have anything organized or anything planned. I have a few things that are saved page-wise and things I want to go through and share with you. So we'll kind of break down some of these fundamentals and understand what these scientists are talking about. What we do have to understand is that from the get-go, that this is a basic standard model and theory. We have to take all this as a theory, of a working theory, and this is the best option that we have to date. Okay, and this is the best way that it all makes sense to the majority of us. Now, there are flaws, and I've tried to mainly point out those flaws in the science and kind of bridge the gap between the public and the scientific community, because there is some things that need to be addressed, and there's questions, and even scientists among themselves question each other and question some of these theories and equations that are used, and it happens. But most of us don't know what happens under the radar, what isn't in the public eye. And a lot of that stuff gets hidden, and a lot of assumptions get made that shouldn't be made. So we're going to break some of this stuff down. So stick with me, and we'll try to get through this together. Okay, so this is the basic periodic table of elements. And I'm going to try to explain to you how to basically read this table. So if we zoom down in here, we see that each element is represented by a symbol. And in this case, hydrogen is represented by the letter H. And up above, you'll see the atomic number, and that is the amount of protons. Now, the atomic weight is down below here, and that is the amount of protons and neutrons together. So to get that, you have to take the atomic weight, we'll just atomic weight and you subtract the atomic number, and then you'll get the amount of neutrons. Okay. Now to let me go ahead and erase this, and I'll show you how to figure out the amount of electrons, because to figure out the amount of electrons is equal to the atomic number minus the charge. Okay. So to get the amount of electrons, it's the atomic number minus the charge. And we'll go over how to find the charge. Okay. Now the different colors, I'm going to discard this. The different colors represent what they are, the subcategories. In the middle, metallized, non-metal type of materials. You get alkali metals, alkaline earth metals, transition metals, lanthanides, actinides, post-transition metals, metalloids, and reactive non-metals, and noble gases. And those are broken down by the different colors. Now the color of name will be the state of matter. So it'll be either gas, liquid, solid, or unknown. And also unknown chemical properties are colored over here, which are mainly your very short-lived radionuclides, your transuranics, your transuranium elements, so to speak. Okay, so let's move over to something that'll explain the charges. So this is what it looks like for the periodic table that explains the charges, and they're in different columns. So your transition metals here in the middle, the charges vary. Okay. Now this will kind of show a little bit better representation of it. So we have over here on the left, where we start, hydrogen is number 1. It has a +1 charge. Okay. And then helium over here, which is the noble gas column, has 0. Then this is +2. And then this one's +3. Now this column here, this will be your carbon column. So carbon's up here. It's said that, get that out of the way, guys. It's said that it's a +4 -4. Okay. And then -3, -2, -1, and like I said, 0. So to get to the electrons, you take the atomic weight, which is the amount of protons, and then you subtract the charge. So we'll do one here. Let's do sulfur. So for sulfur, it has an atomic weight of 16, and the charge is -2, so you subtract -2. And in math, 2 negatives is a positive, so it'll be 16 +2, which will be 18. Sulfur has 18 electrons. As I said, the transition metals are in here, and they vary except for these here, this +2 and this +1. Zinc, cadmium, and silver, they always have +1, and these always have +2. Oh yeah, I found this too. I thought this was kind of interesting. This is kind of a periodic table, and it's based off of using the Schrodinger equation, and it's kind of set up for the orbitals, and which we're going to get into. And it's a lot what this video is about, is the orbitals, electron orbitals. Now I wanted to explain how, since we know everything is based off the atomic number and the atomic weight and the amount of protons and neutrons there are on the periodic table, then how do they know how many protons are in each element? Well, this kind of explains it. And the way I understand it is, long ago, when they were making the periodic table, they basically used a cyclotron, and it's based off of an electron volt, and using a magnetic field. Okay. Now, let's explain the electron volt, because that's part of areas that can be questioned. And I'll explain that. I have that somewhere. Before we get to this here, let me go find the joule. Okay. Now the electron volt, let's draw in this one here. 1 electron volt is equal to 1.602 times 10 to the -19th is 1 electron volt. And that's in joules. Now we see the correlation here between the joule. Now, the International System of Units says that, back out of here. So everybody know what 1 electron volt is? 1.602 times 10 to the -19 joules. This card. Okay. Now 1 joule, the International System of Units says 1 joule is equal to the amount of work done when a force of 1 Newton displaces a mass through a distance of 1 meter in the direction of the force applied. Let me read that again. It is equal to the amount of work done when a force of 1 Newton displaces a mass through the distance of 1 meter in the direction of the force applied. Well, I think there's a few things that could be questioned here. Of course, the amount of work, I think everybody can constructively say that seems strange. The amount of work done when a force of 1 Newton, which is another measurement, that Newton displaces a mass through a distance of 1 meter. Now the 1 meter I have an issue with, which most people wouldn't even have an issue with, but 1 meter is a distance using an apparatus, say a yardstick or a meter stick, or 3 feet in a meter. And that apparatus has lines on it that has a thickness. Even minuscule thicknesses. Okay, so that is one where there's assumptions made, there's averages made, and that happens a lot where averages are made, or even, it's rounded up to the next number, whole number. Okay, so that's what a joule is. Is equal to the amount of work done when a force of 1 Newton displaces a mass through a distance of 1 meter in the direction of force applied. Okay. It is also energy dissipated as heat when the electric current of 1 ampere passes through the resistance of 1 ohm for 1 second. Okay, that's a whole nother discussion there. So what we're going to do here is we're going to get back to periodic table for a moment. Okay, so we've figured out now that the way they've done the periodic table is that they've somehow come to an understanding of what the atomic number is, which is represented above the number, or above the letter, the symbol of the element. Okay, and that's how they've figured out everything else, basically. Okay, now how do they get down to these protons? How do they know how many protons are exactly in the nucleus? Well, as I explained, they use a cyclotron or a mass spectrometer. Okay, and that's what I found this. This is what this person explains. What they do is one can do it fairly easily with an ion accelerator and a magnet. With the right setup, one can get a beam of monoenergetic ions out of the accelerator, send them through a stripper, electron stripper, to remove the electrons, and then send them through a magnet to separate the components out by velocities, which depends on the ion mass through the energy. Okay? From the magnet deflections, one can get a charge to mass ratios and get back to a number of protons, charge on a fully stripped ion, and a number of neutrons from a number of protons and the mass. This is the heart of the mass spectrometry. This is at the heart of mass spectrometry, although one can use time of flight techniques rather than or in addition to magnetic separation. Okay, now let me explain a few of these concepts that some of you may not know. There's a few words in here. So we have mass spectrometry. Okay, and the way I understand it, here I'll get my drawler out. And the way I understand it is, let me get back to white here, is that you have a basic magnet, okay? And this is the way it's kind of set up. Okay. Now, this is a magnet, okay? And there's a voltage put through this magnet. And then, well, let me do this better, to be honest with you. I could do this better. This would be easier. Let's go this way. Let's just do it this way, okay? And what they do is they send the sample, the ion, okay, the element, through, and they try to see how it curves. And that curve tells them the weight of the ion. So the differences they can figure. That's how they figure the differences in the charge, in the electron volts. and the radius. So basically, whatever radius this curve takes, you're figuring a center point, and we'll make the whole circle, right? So that radius tells them what that element is. So then another element would go through there, and it would do this. So then you make, you know, the full circle, and that's what that element signature would be, and so on and so forth. You'd have some that just, you know, pass straight through, don't do anything, no charge. Okay. So now let me kind of explain how a cyclotron works. Okay. And this is going to be, well, first I'll show it in the side view, and then I'll show it from the top down because it'll be easier. So side view, excuse my, I'm not an artist, but I'll do my best here. Okay, so the side view, so top and side view basically. Okay, this is curved. This is curved. Okay. Right. Doing the best I can, guys. Okay. So I know that's not quite right. So, but think of these as two hemispheres, okay? Two hemispheres. And you gotta figure that there's a whole setup around this apparatus, okay? There's a whole setup. But there's two hemispheres. I want you guys to understand there's two hemispheres here. So when I draw it from the top view down, you'll understand what I'm saying. And then what they do is they add a voltage to these two planes. Okay. Say, I think there's, the old ones was like 18 MeV. Okay. Don't quote me on that, but it's probably a pretty standard amount back then. So what they do is they put the voltage across these planes, okay? And then they have a magnetic field from underneath that flows upwards. Across the entire area, okay? So, now that you understand that, let's try to do, I'll keep that going. We'll do the side view over on the other side. Okay, so we got our two hemispheres, right? And then your magnetic field coming from underneath around the whole area, right? Okay, so what they do is they interject this particle into there, and they turn on the voltage on one plane, and they have the opposite polarity on the other. So it's attracted to one side or the other depending on its charge. So when it comes in, okay, they turn this side off and turn this side on. So then it is attracted to this side. And when it gets over to this side, they shut this side off and turn it back on this side, which creates it to come back around. Maybe I got this wrong here. Let me kind of fix this because I do have this wrong, guys. Sorry. Technical difficulties, don't you love it? Okay, let's get back to the initial two hemispheres. Okay, so it comes in and it comes this way, okay, and it comes out further. Okay, then switch it. So it's attracted over here, okay? And it comes over here, and then they switch it again back over to here. It comes back over, and then they switch it again. And it just keeps on making this swirl, and then finally it gets ejected, okay? Now this whole time it's accelerating. Each time it changes polarity and comes across, it increases its velocity. And there's formulas for all this. I can share them if you guys want to know. Down in the comments I'll share what their names are and how they're written out. I'm not going to go through that, but I'm just trying to go over the basics here. So this is how this works. Okay, and the masses are different when a specific voltage is used and the magnetic field a certain magnetic field is used. So you can measure those differences, and you can figure out that those heavier things have more protons, has more mass, has more nucleus, has more atomic weight. So that's how they figure the differences of the different elements for the periodic table, and they put the amount of protons on there. Okay, so this all is based off of the electron volt, the joule, the newton, the distance and work done in a meter, and probably a lot of other flaws and rooms for error that isn't really explained to most people. Even I don't know. I'm just trying to, like I said, I'm just doing the best I can to explain the basics here. Okay? So now that we got that sorted, let's see where we are at. Okay. So let's figure out the electron stripping, okay? How they get down to the protons. And this is done. This was released from Division of Nuclear Physics, 1 Institute of Technology, box 118, SE 221001, Sweden. Okay. Sweden and South Wales, Australia. Charge exchange processes. Charge exchange processes, where the capture or loss of electrons in a target medium changes the electrical charge state of swift ions, are of central importance of electrostatic tandem accelerators. For example, such processes are employed for the formation of negative ions prior to injection into the accelerator, which is commonly used to produce helium negative ions, and in this case involves the double electron capture by low energy helium positive ions and alkali metal vapor. The conversion of negative or positive ions by stripping electrons from the injected negative ions by a target medium in the high voltage terminal of the tandem accelerator. So it's the basic same principles of the cyclotron. They're accelerating the particle, and they're stripping the electron. Okay. The latter may improve the suppression, or wait a second. Okay. The conversion of negative to positive ions by stripping electrons from the injected negative ions by targeting. Okay, I'm sorry, I read that. The second stripping of positive ions to create highly positive charged states, either at some point along the high energy tube of the tandem accelerator, or often acceleration. The latter may improve the suppression of background ions by analyzing magnet, or may be required to match the ion charge state with that required by a second accelerator, such as a cyclotron. Okay, so basically they're doing the same thing, but they need to match it with the cyclotron to make sure that both answers are the same. Okay. Fragmentation of molecular ions in the high voltage terminal of the tandem accelerator. This is the crucial tool of accelerator mass spectrometry discussed in chapter question mark. It can also be used to produce beams of elements which do not form stable negative ions. A typical example is 14N, which for example may be accelerated by injecting the molecule ion 14NH negative into the tandem accelerator. Electron stripping in the high voltage terminal then renders the molecular ion unstable and releases a positive nitrogen ion. So that's how the electron stripping occurs. Okay. So you see these bins. That's basically your frequency, your frequency of change. When it goes through those magnets of that cyclotron, it creates a frequency, sort of like, box. Oh, shoot. Let me erase this. That'll be your frequency. That's how you know your differences. Right? Understand that frequency? Yep, okay. So, what else do we have for you? Yes, this is the main talk we're trying to get to. Electron orbitals and quantum numbers. Okay? So, protons, electrons, neutrons. We've discussed the flaws, discussed room for error. We've discussed some of those things. Now let's discuss electrons, quantum numbers. Okay, course concept. In this tutorial on quantum numbers, you will learn how we can describe the properties of an electron in an associated atom. These various properties include energy level, shape, orientation, and spin. You will also learn about orbital shapes. Now, there's some things I want you to guys, basic principles and understanding. Okay, so what I'm going to add here is we're going to do Casimir effect. Van der Waals forces. Dipole. I think of a sphere. The dipole. Angular momentum. And magnetic moment. So, spin. Okay. And the spin usually is done through half spin, negative half spin. Okay. So look these things up. I'm not going to go over these things in this video, but check out these things. This kind of ties all into everything here. Okay. Topics covered in other articles, vocabulary. Nodes is equal a point or plane of zero electron density. Okay. point or plane of zero electron density. Introduction to quantum numbers and orbital shapes. Quantum numbers are used to describe atomic orbitals, regions of space in which an electron can be found. From these numbers, we can determine the different properties of electrons in an atomic orbital. It is important to note that each electron will be unique to another, according to the Pauli Exclusion principle, which we'll go over. For this to be true, no two electrons in the same atom can have the same four quantum numbers. Okay? The principle of quantum numbers. So we can't have the same four of these quantum numbers. The principal quantum numbers, n, describes the electron shell or size of an orbital. An electron shell can be thought of as a part of an atom where an electron orbits the nucleus. Learn about Rutherford discovers the nucleus. The only allowable values of n are whole number integers, starting with 1, which are whole numbers. There's no decimal point or fraction or none of that. Okay? A higher n value means that the associated electron is further away from the nucleus. For example, an electron with n equals 1 would be much closer to the nucleus than an electron with n equals 5. When comparing electrons with the same L, we can also say that the electron with a higher n value is higher energy. With the higher n, an electron will not feel the attractive pull to the positively charged nucleus due to its further distance. The electron's negative charge is not stabilized, so the electron is higher energy. And even these graphs, I mean, this is not really what it looks like. I mean, this is a two-dimensional representation, and it's just difficult to explain. But that's the problem. Therein lies some of the problems and the difficulty in explaining it and trying to get everybody on the same page about it. Okay, note, in actuality, electrons are not fixed, but are represented by something called an electron cloud. Represented, okay? However, the image above clearly shows the concept of different electron shells, the inner circle being N1 and the outer circle being N2. As we increase in N, we move further away from the nucleus. Okay? There are 4 different kinds of orbitals, which are named S, P, D, and F orbitals. They each have a different orbital shape. An S orbital is spherical with the nucleus at its center. A P orbital is a dumbbell shaped, and 4 out of 5 D orbitals are cloverleaf shaped. The last D orbital is an elongated dumbbell with a donut around its center. The angular momentum quantum number describes the subshell, or the shape, of an orbital and its allowable range. There are 4 distinct shapes to remember: the S, the P, the D, and the F orbitals. The value of the L assigned to each L subshell is based on the number of angular nodes, planes. For S orbitals, which are spheres, there is no angular nodes. So it's either I or L. I'm not quite sure, to be honest with you, but I think it's L or I. I'm not sure. For P orbitals, which has electron density separated by 1 angular nodes, I or L is equal to 1. I think it's L. Following this trend, D orbitals would have L equals 2, and F orbitals would have L equals 3, as they have 2 and 3 angular nodes, respectively. Angular momentum. As pictured above, the S orbital has uninterrupted electron densities, or density all around. So L is 0. The P orbital's lobes are separated by a nodal plane. Okay, that X plane there, which is oriented along the x-axis, making L equal 1. And the D orbital has 2 nodal planes along the x and y axis, which assigns L equals 2. try drawing an f orbital and make sure to include the 3 angular nodes, L equals 3. The magnetic quantum number describes the various orientations of subshells in 3D space. Magnetic moment. Its range is negative L or L, meaning that for how many ways you can uniquely rotate a certain shape, you have that many possible M values, because there's not a new distinct orientation when you rotate a sphere around the origin. The s orbital will only have one possible magnetic orientation, but due to the angular nodes of the p, d, and f orbitals, they have many possible M values as indicated in the diagram below. M is 0, M is 1, M is 0, M is 1, M2, M1, M0, M1, M2, and so on and so forth. Those are for the different orbitals. The spin quantum number. The spin, the dipole. The spin quantum number describes the spin of a certain electron in an orbital. The spin is either plus or negative a half, which denotes either an upspin or a downspin. Each orbital can hold a max of 2 electrons, and if fully filled, the electrons cannot share the same spin direction. If electrons do not point in the opposite direction, then it would be a violation of the Pauli Exclusion principle. 2 electrons cannot share the same 4 quantum numbers. If the orbital is not fully occupied, then the electron can take on any spin direction. Convention usually assigns the upspin first in a non-fully occupied orbital. Convention usually assigns the upspin first. Usually. Okay. Now, I wanted to move on to electron orbitals and orbital shapes. Electron orbitals are the 3-dimensional areas around the nucleus of an atom where the particular electron resides. Each orbital can hold 2 electrons. They are also known as atomic orbitals. Atomic orbitals come in different shapes depending on number of electrons and the atom has. The number of electrons the atom has. We will learn about the s orbital field. We already did, didn't we? Yeah, we pretty much just went over the same thing. It just kind of shows it a different way. So, how to write an electron configuration. Okay. Concepts. In this tutorial, you will learn how to find and write the electron configuration in an orbital diagram for various elements using the periodic table. You will learn Aufbau's principle, Hund's rule, and the Pauli Exclusion principle. Enjoy this tutorial. Be sure to check out our others linked below. And also, yeah, while we're at it, we're at this chemistrytalk.org, and they've done pretty well. So go ahead and check them out. They got a lot of stuff that's pretty cool. Okay, electron configuration is a description of where electrons are in a molecule or atom. Electrons occupy orbitals that have characteristic levels of energy. Systems with a greater number of electrons will occupy a greater amount of energy levels, meaning that they also will utilize higher energy levels. Electron configurations are represented by standard written notation or by using orbital diagrams. Electron configurations have a standard notation that tells you the principal energy levels and sublevels that electrons occupy. Here is the electron configuration for helium, 1s2. The first integer, 1, gives us the principal energy level. The letter S represents the type of orbital which we went over, and the subscript 2 gives us the electron occupancy in that orbital. In this case, there are 2 electrons in the s orbital with the principal energy level of 1, which is helium. Systems with the greater number of electrons will occupy a greater amount of energy levels. The electron configuration for lithium is 1s2, 2s1. Lithium, containing 3 electrons, has 2 electrons occupying an s orbital at the first energy level and 1 electron occupying an s orbital at the second energy level. Okay. The periodic table is a helpful tool in writing these configurations. Principal energy level is indicated by the integer 1, 2, 3, so on, that corresponds with the periods on the periodic table. Each successive integer generally represents a higher energy level than the last. Sublevels are indicated by the letters S, P, D, and F. Groups or blocks of the periodic table share the same sublevel and are divided as seen in the following diagram. So now you guys can understand that it's broken down and how the shape of the periodic table was actually made. It's based on the electron orbitals, okay, and the charge of the element. Okay, to find the electron configuration of an element, start at hydrogen and trace across each period until your target element is reached. So you start at the left at hydrogen, and you work your way over to the right, which would be helium, and then you have to start all the way back over to the left again. Okay, and then you'll get to lithium on the S block. Once again, we will be using lithium. We start with our attention on hydrogen, move to helium, and then to lithium. The electron configuration for lithium is therefore 1s2, 2s1. Doesn't that just sound perfect in how this all should work? 1s2, 2s1, 1s2, 2s1. Yeah, I think there's room for error. I think there's room for assumptions. I think there's room for approximations and such. Okay. So we've pretty much figured that out. That's how that's worked. Bromine, they go over different ones and how to represent those. Okay. Aufbau. Aufbau is German for building up, so this rule dictates how orbitals are filled based on their energy states. The principle states that the lower energy electron orbitals will fill up before higher energy orbitals. So the 1s orbital will fill before the 2s orbital, and the 2s orbital will fill before the 2p orbital, and so on. However, the 4s shell will be filled before the 3d shell because the 4s shell is lower energy than the 3D shell, which is kind of strange, isn't it, guys? I mean, however, the 4S shell will be filled before the 3D shell, which is going against the rhythm that is occurring, and it will be filled before the 3rd shell. Okay, and in the example below, configuration A shows a fully occupied 1s orbital and a half-occupied 2s orbital. Configuration B shows a half-occupied 1s orbital and a fully occupied 2s orbital. Based on Aufbau's principle, which do you think the electron configuration of lithium? Since the 1s orbital is of lower energy than the 2s orbital, the 1s orbital should be filled first, and any remaining electrons should be used to fill the 2s orbital, making configuration A the correct orbital diagram for lithium. Hund's rule dictates how orbitals of the same energy should be filled. 1 electron is given to each of these orbitals before 2 electrons can occupy the same orbital. Single electrons will also have the same spin, indicated by the direction of arrows in the orbital diagrams. Same spin. Okay. I want to go over the Pauli exclusion principle. Pauli exclusion principle states that in any atom, no electron can have the same 4 electronic quantum numbers as another electron. Every electron must have different quantum numbers. So in each electronic orbital, in LM, there can there can be two electrons and they must have different spins. One electron will have m equals plus half, and the other will be m is equal to negative half. Therefore, no two electrons will have the same four quantum numbers. The spin quantum numbers was added to the previously discovered three quantum numbers n, l, and m by the Pauli Exclusion principle. The positive m, ms, usually indicates spin up and is represented by an upward pointing arrow. A negative ms, I think that's ms, usually indicates spin down as represented by down facing arrow. The spin quantum number is slightly different from the other quantum numbers because it is not dependent on them. It can only have a value of plus half or negative half, and these values are independent of all other quantum numbers. The other quantum numbers are all interconnected. The principle also defines that each orbital can only have two electrons. This definition originates from an orbital being defined by the first three quantum numbers. The remaining quantum spin number only has two possible values. Therefore, according to the definition of the Pauli Exclusion principle, the orbital can only hold two electrons. Fermions and bosons. This principle applies to all fermions. A fermion is an atomic particle that has a half-integer spin. Commonly known fermions are electrons, protons, and neutrons. Therefore, all these particles will follow the Pauli Exclusion principle. The alternative to fermions is a boson. Bosons have integer spins. The most common boson is a photon. There can be many photons in one energy state. In one state, they all have the same quantum number. This is a violation of the Pauli Exclusion rule. Since photons are bosons, however, they do not follow the Pauli Exclusion rule. So, I think I threw a lot at you today. We got into electron orbitals, we got into the periodic table, we got into how protons and neutrons are shown, cyclotrons. We covered it quite a bit, so I guess we'll call it a day. And if you guys have some comments or questions or anything you want to say, just comment down below. I would prefer if you subscribed if you're not, and if you can give my video a thumbs up, that helps a lot. It helps me get more views. So if you guys want more content, more views, you want to see more from me, please give me a hand, give me a thumbs up. So I'm trying to teach you guys something, I'm trying to learn something myself, so we're all going about this together. So alright guys, well I appreciate your time, and check you guys later. Bye.